Okay. So another example. Amelia walks briskly at 6 kilometers per hour. When she walks at this rate, for 2 hours, she burns 454 calories. Bruce walks slower at 4 kilometers per hour. Burning 62 calories in 30 minutes. If Amelia walks 3 hours, how much longer will Bruce have to walk to burn the same calories, same amount of calories? Okay. Okay, so quite often, especially in applied, you'll get a longer word problem, and so it's up to you to interpret it and see what you need to do, right? Like read it, it's like how do we approach this? And one of the frustrating parts will be that it's not a cookie cutter approach, right? It's not like, hey, look at this trinomial, factor it, right? It's basically the same steps all over again, right? You just need to know how to do it. With word problems, you need to be able to see how am I going to organize my information and what do I need to do first. And so there will be, and you've already noticed it, more than one way of solving things, right? And so when I do an example, it's not necessarily the only way, but it is one way perhaps to get there, right? So keep that in mind. And if you want to try it your way later and you get the same answer, you most likely you're going to be right. Okay. Okay. So we have Amelia, and she walks 6 kilometers an hour. At that rate, if she walks at that rate for 2 hours, she'll burn 454 calories. Right. Bruce is a little slower, walks slower, 62 calories burnt in 30 minutes. Okay. If Amelia walks for 3 hours, how much longer will Bruce have to walk to burn the same amount? So in this case, the speed has nothing to do with anything, right? Like the speed is just given to you as a reference, but it's a bit of a TMI, too much information, right? So what we want to do here is figure out how many calories, right? Step 1, calories burned by Amelia, right? So after walking for 3 hours. So I'm going to use proportional reasoning here because you're given a rate, right, that after 2 hours, right, she burns 454 calories. And therefore, on the other side, I'm going to make sure my hours, which is 3, are in the numerator, and I'm going to figure out the number of calories that would be associated with that. Okay, you cross multiply. So it's 3 times 450, actually no, sorry. It's x times 2, right? And then it's 454 times 3. And we want to isolate x. So we divide both sides by 2. Canceling out the 2's there. And so you get the number of calories. That's 681. 681, no decimals, but we could have had decimals because calories, right, can be, it's a continuous data, right? So this is how much she will burn. So now we need to figure out, now you're gonna have to cross and check out what Bruce will have to do to get the same results, right? So Bruce will need, right, X hours, right, or minutes. So I'm going to kind of break this down here. And I'm going to start with a fact, right? I know that Bruce, after 30 minutes, he burns 62 calories. It's important that you notice this. In this case, there are no decimals. But if there are decimals, we use at least 4 while we're working. Okay, don't round to 2 here and then use it for your second part. But I'm going to use this 681 over here. Right. I don't know if this is going to make it a little messy, but oh yeah, super messy. But anyways, that way you know, right? The 681, I carry it over to here. I know the rate that Bruce burns calories at, and I'm going to figure out X number, and this is going to be in minutes. You could have put down half an hour, that's fine, but the question doesn't specify whether it should be in minutes or hours. I will do both probably. So you cross multiply there. So it's 681 times 30, right? This times that. And on the other side, you have x times 62. Divide both sides by 62. Cancel. And you have to be comfortable with the variable to be on the right side. We're always used to it being on the left side. It really doesn't matter. Okay, so 681 times 30 divided by 62. So that's 329.51 minutes. Okay. So if you're tempted to conclude here, you need to read the question carefully. Okay, it says, how much longer will Bruce have to walk? How much longer compared to Amelia will Bruce have to walk, right? And so you got to do a little bit of work here or show that 3 hours would be equal to 180 minutes, right? If you 3 hours is 180, so it's how much longer than this will Bruce have to walk, right? Difference is 329.51. I think it's okay to round there, but let me just write down 5161. Let's do that here. If you round to 4 decimals, you're safe. 5161. So 5161 minus 180, that's 149.5161 minutes. Right? So are we following that? Am I going too fast? I hope I'm not going too fast, right? But let me reiterate. What am I doing here? 680, we figured out how many calories Amelia would burn in 3 hours. Then we brought it over to this side, knowing that Bruce burned 62 calories in 30 minutes. We figured out the total time he would need to burn that many calories. And now we're figuring out how much longer than Amelia would he have to walk. And the answer is 149.5161 minutes. So we can say Bruce would have to walk an extra, and now I'm going to round here, 149.52 minutes to burn 681 calories. This is really what this question was after. So if you need a little bit more of this type of question, look at the worksheet that I gave you. The back side in particular has some word problems as well. That way you can, and I get it that this was a little bit of a loaded question. So you most likely on a test or quiz, it will be A, B, right? Like it'll break it down into steps, right? But you should be able to do something like this as well. All right. Okay, let's dive into 8.3 now. I just wanted to have one more example. Okay, working with scale factors. First of all, some definitions here or some key terms. Scale diagram, a drawing in which measurements are proportionately sorry, this is just an L here followed by a Y, proportionately reduced or enlarged from the actual measurements. So it's a drawing in which the measurements are proportionately reduced or enlarged from the actual measurements. Okay. Two objects are said to be similar if all dimensions are affected by the same constant. This is very important, right? I'm going to put that in quotations. Right? Two objects are said to be the same if every dimension has been affected by the same constant. Okay, so for example, if you have, let's say we have an equilateral triangle, right? This is 10 centimeters, 10 centimeters, 10 centimeters. Do you remember what all angles in an equilateral triangle will be? All together 180, but each will be 60, right? They'll all be the same. Do you remember that? So 60, 60. Okay. So if you notice that there is a larger triangle that has, obviously the shape would have to be the same, right? And you see that it's 20, 20, 20. What are the angles going to be of this enlarged triangle? Still 60, right? It doesn't matter what the size is, it's always 60 degrees. Okay? So every single dimension has been affected by a factor or a constant of 2. This, it could be that it's times 2, it could be times 3, it could be times 2.15, it could be a third, a quarter, it doesn't matter. It's going to be affected by the same constant, and all angles are going to be congruent, right? So this is the, let's call this the original, and this would be considered the diagram. So you start with one, and then you either get a larger version of it or a reduced version of it, right? But we always have the original and the diagram to compare to. Okay. Scale. The ratio of a measurement of a scale diagram to the corresponding measurement on the actual or original object. The ratio of a measurement. So it's always stated like this. Always stated like this. So you can have diagram actual or new and original. when is one better than the other? I would have both of them on my study sheet, but sometimes when you're looking at right, the picture of something, right, you obviously know that the picture is the diagram and the actual scenery would be the actual thing, right? But sometimes you're just making a copy of a shape. So let's say you're making a copy of a triangle, then it's best to use new and original, right? Because you have the one you started off with and the new one you made. So that's why I do both, right? One thing you need to add, if units are different, they need to be included. Right? So make like this is just an important note, right? If the units are exactly the same, if you're talking inches, you actually don't have to have the inches even stated. But if they are different, like on a map, they're not different, they're not the same, sorry, then you would include the measurements there, okay? Example, 1 centimeter, it represents 50 kilometers, so this would be on a map. So on the right side, this is the actual, and this is the diagram. Always keep that in mind, right? So we always look, we start with the actual and we look to the left to see what happened, okay? So in this particular scenario, 50 kilometers, and you're going down to 1 centimeter, so this would be a reduction, okay? Represents a, use a red pen here, reduction of the actual or the original. Okay. Then if you have another example here, where let's say you have 1 centimeter on the left and you have 0.1 millimeter on the right. Again, this is the diagram and this is the actual. So this would be a cell, right? Or something very small that you're zooming in on. Obviously, the diagram would now be an enlargement of the actual object, right? So you start here and you look to the right, and so this is represents enlargement of the original or actual. So you have to be able to tell me just by looking at it what happened, right? If we had more examples, right? 2 to 5, obviously they have the same units. This would be a reduction. Reduction of original, or of actual. If you had, right, enlargement. Because you went, this is the original and you went, so the diagram will end up being enlargement of original. So no units, meaning the units were the same, you cancel them out. That's actually what happens. If you happen to have the same units, you can cancel them out and just end up with numbers like that. Okay? Okay, working with scale diagrams. I see you guys taking notes, and make sure you do that, right? Don't just hope for the best, right? You're gonna have to go back to these notes and study off of them, okay? The dimensions of a room are 12 meters by 8.6 meters. It's basically saying the room measures 12 by 8.6, right? Draw this room using a scale of 1 centimeter to 2.2 meters. Steps. Convert actual dimensions, right? Draw draw object using conversions. And then 3, label object with actual measurements. It could be that the textbook doesn't, but that's technically what happens in real life. You don't label that object that you just drew with the actual measurements. You label it with you don't label the measurements you just converted. You use the actual measurements in real life. You put them on the diagram. Okay, that's why I give you these steps. So let's go ahead and so we'll convert. So basically what happens here is that if 1 centimeter is 2.2 meters, right? And you're going to calculate, right? How many centimeters would it be for 12 meters? Okay. So you cross multiply. Okay, so that's 12 times 1, it's 12, right? And x times 2.2, you divide both sides by 2.2. So it's essentially 12 divided by 2.2, which is 5.45. And here we can round to 2 centimeters. Okay, this is the length of our object because it's the longer side. We're just going to call that the length. And then we use the same scale factor or scale here. 1 centimeter is equal to 2.2 meters to convert the width, which is 8.6 meters. So we're going to call this y in centimeters. Let's multiply like that. So it's really just 8.6 is equal to x times 2.2. Divide both sides by 2.2. And so it's really 8.6 divided by 2.2, and that's 3.91 if you round. This is the width. Okay. And so we will use these to draw. Okay. And you may not have a ruler. I will not. I would like you to just have one ruler. I asked you to have one at the beginning, right? And so we will draw this. So I'm using 5.45 centimeters to draw the length of this. So you have to make sure you have enough room, right? So if I start here, 5.45 is almost, you start here. And again, I'm not going to split hair over this. Like if you're too close to 5.5, not a big deal, right? And then this is 3.91. So 3.9 is good enough, right? So you go 3.9 up like that. Try your best to keep it at a right angle. This should be, this is close, it's 5.5 at the top, not a big deal. So this is 12 meters by 8.6 meters. Okay. Label using actual measurements when you label it. Okay. Okay. So I'm gonna ask you to try page. So write this down. We'll scratch this for now. We're gonna go booklet, page 2. And hold on. I'm not quite at scale factor yet, so that's why this is a bit of a problem. Page 4, question 4. Yes. Page 2 is just review stuff, right? So